Okay, if you're watching this, we'll have done what I'm talking about right here in class. We're going to look at the Delta Math stuff, see if it made sense. If not, we're going to hopefully fix it. But we're just going to, for the video, I'm just going to keep going. So we talked yesterday about domain and range, how to tell if a relation's a function. Going to continue on that line of thought, I guess. So here's the next thing. Again, vocabulary heavy here at the beginning. Independent variables versus dependent variables. So the variable, I'm going to read to you, sorry. The variable that represents the input values. So whatever you're inputting, those are your independent variables because you pick those independently on your own. You put whatever you want to in there. It can be anything from the domain. And then the variable that represents the output, we call the dependent variable because it depends on the value of whatever you plugged in as the independent variable. And so when we write an equation, a lot of times we want to put the y over there by itself because we're going to treat that as the dependent variable. So if we say y is a function of x, that means we're going to plug whatever x values we want to in here. And whatever I get out for y depends on what I plug in for x. And I'm only going to get one output value. One output value for every independent variable that I put in, every domain element, every input. So here's this one. It says y equals negative 3x plus 12 represents the amount y in fluid ounces. Okay, so y is the amount in fluid ounces of juice remaining in the bottle. After you take, this is x is the number of gulps you take. So it says identify the independent and dependent variables. Well, y is a function of x. So x is the independent variable. The dependent variable is the y. Okay, and then your domain is 0, 1, 2, 3, and 4, which basically is saying you can take no gulps, 1 gulp, 2 gulps, 3 gulps, 4 gulps. And apparently that's the only things in the domain. Oh, wait, I didn't need to put I don't know why I've got an AN symbol right there. It does not need to be there. You just need to have the comma because it's the set that has this. What's the range? So if we just take, and here's how people write it. I want to know what y is when I plug a 0 in. So I get 0 plus 12. So one of my output values, there's 12 fluid ounces left in that bottle when I start. When I take 1 gulp, I'm going to have 9 fluid ounces left. When I take 2 gulps, I'll have 6 fluid ounces left. When I take 3 gulps, oops, there's 3 fluid ounces left. And when I take 4 gulps, what am I doing? Oh my goodness, it's a long day. There's 0 fluid ounces left. So the range can either be 0, 3, 6, 9, or 12. Okay. All right. A linear equation in 2 variables, x and y, is an equation that can be written in the form y equals mx plus b, where m and b are constants. So this is a linear equation. If you can make it look like y equals mx plus b, which tomorrow we'll talk more about what y equals mx plus b means. But if you can convert a line into that form, it's a linear equation. So the graph of a linear equation, is a line. Likewise, a linear function is a function whose graph is a non-vertical line. So what they're saying is like if we had an xy axis, that's a linear equation. That's a linear function. If you had just a horizontal line, that's one. Put x's and y's on those. If you had one that goes downhill, linear function. But notice how it said it's a non-vertical line, because if we drew, here's x and y, if we drew a vertical line, it wouldn't pass the vertical line test. Like, we'd have all kinds of outputs for that one input. That's why it says it's a non-vertical line. So a nonlinear function does not have a constant rate of change. So its graph is not a line. So it's something that a nonlinear function can't be written like this. And what they mean by a constant rate of change is like some of the ones we were talking about yesterday where the x went up by 1, but the y went down by 2, and that always happened. So pretty much, please don't make this difficult. Does the graph represent a linear or nonlinear function? On A, is that a line? No, that is a curve. So this is a nonlinear function. This is a linear function. And what they're talking about with the constant rate of change, let me change colors. Say you find 2 points on that line. As I move across it from left to right, I go over 1, up 2, over 1, up 2, over 1, up 2. That's what they mean by the constant rate of change. Like for every increase of 1 in the x, I'm going to increase 2 on the y. Okay. Then sometimes they'll give you tables where there's not a picture and ask you if it's a linear function. So we're hunting for that. Is there a constant rate of change? So look at your inputs. Look at your x's. From 3 to 6, I go up by 3. From 6 to 9, I go up by 3. From 9 to 12, I go up by 3. So I've got a constant, steady increase of 3 with the x's. For the y's, I went down by 6, down by 6, down by 6. So the question is it linear or nonlinear? This represents a linear function because there is a constant rate of change. Okay, now up here though, I went up by 2, up by 2, up by 2. So my x's are changing the exact same way. For it to be a linear function, the y's have to change in the exact same way. So this went up by 7. Ooh, up by 11. Right then. I don't even care what happens on the next part. This is a nonlinear function because there's not a constant rate of change. Okay. All right. Which of these represent linear functions? So remember, a linear function can be written in this form right here. So could you make this look like that? There'd be no x's, but there's a 3.8 at the end. That is a linear function. This, I can't make a square root turn into a plain old x. Not one. 3 to the x can't look like that. 2 over x can't look like that. Okay, now this one, if I were to distribute the x, ooh, now it does look like that. That's a linear function. And I can't get an x squared when one doesn't exist. So we got 2 of these are linear functions. And then this was just because I thought it was a nice picture. It was like it sums up what we know about functions, where you say, oh, we can talk about it in words, or we've got equations, we've got tables, we've got mapping diagrams, we've got graphs. So that's just in there for you to have it in your notes. And then the last thing we're going to do today is we're going to make T-charts. Or you could do the input-output table if you like running your data horizontally. We're going to take this equation, which is a linear equation, because I can write it like that. It's written like that. There's some number x plus some number, okay? Now I'm just going to figure out some points that I can put on here. So if I plug in a 0 for x, that gives me 0 plus 5. If I plug in a 1 for x, that'll give me 2 plus 5. If I plug in a 2 for x, 4 plus 5. See what's happening? They're always going up by 2. So if I plug a 3 in, I'll get an 11. If I plug a 4 in, I'll get a 13. And these are all points on the graph. 0, 1, 2, 3, 4, 5, 1, 7, 2, 9. Now, these next two I found, they're running off the page. So what if I went the other way? What if I did -1? So that's -2 plus 5. There's a 3. If I kept going, I'm getting -4 plus 5. There's a 1. So I plug -1 in. I'm getting 3 out. -2 in. I'm getting 1 out. Now we can see our pattern. So for every one space I went to the right, I went up 2. For every one space I go to the left, I'd be going down 2. So I can just take and find those points without making the t-chart if I want to. And then when it says graph the linear function, that means you're doing, like we just did it for these particular, oops, it's not drawing. For these particular x's that I chose. But I could have done it for, 1.7, and that point would have been on there. So we just connect them so that we're including everything. Okay, and then one more. Make a t-chart or an output table, whichever one you like, to do this. Okay, now remember our x's are independent variable. So they're the ones that we choose independently. Look what's going to happen. I'm going to put definitely a 0 in there because that's easy. Because that'll give you 0 minus 3, that's -3. Okay, but I get to choose the x's I want to put in there. Whatever the x is that I pick, I'm going to half it and then subtract 3. So why not pick even numbers? Because they're easy to half. Half of 2 is 1. 1 minus 3 is -2. So over 2, down 2. And we'll keep going. Half of 4 minus 3. 2 minus 3 is -1. So I've got the point over 4, down 1. Half of 6, down 3. That's 3 minus 3 is 0. Okay, you see the pattern? For every 2 I go to the right on the x, I go up 1 on the y. Go over 2, up 1, over 2, up 1. Because it's a linear function. It looks like that, where m is the half and -3 is the b. If I went the other way, let's say I chose -2. I'm going to get a -4. But that's exactly where I thought it would be, because I got to follow this pattern. So I'm going to go 2 backwards and down 1, 2 backwards and down 1. So I've got that constant rate of change. Oops. And then I've got my line. Okay, so tonight's homework, I'm figuring you may have had a little trouble with the Delta math, figuring out exactly what you're supposed to do. So tonight's homework's not too awful bad. It's going to be a worksheet. You're going to check your answers on Google Classroom, and then you're just going to make sure you got the Delta math stuff done.